Hello, my 11th standard warriors. Welcome to the Nurture series. Hi, Saja, Varun. Welcome, Ishpreet. Hello, good evening, my warriors. Nurture series is for all the 11th standard students, and even a 12th or a dropper student can definitely watch it if you want to revise and if you have skipped this topic when you are in 11th. And today we are going to talk about, excess pressure in drops and bubbles, and also the capillary effect, angle of contact, all of this. These are all a part of fluid mechanics. We started with lecture 1 on hydrostatic pressure, barometer, etc. Then lecture 2 on buoyancy. Then we went to lecture 3 with Bernoulli's equation of continuity. Then we went to viscosity. Then we came to surface tension and surface energy in the last lecture. And today's lecture we are going to see with me, all right, excess pressure in water drop, air bubbles, soap bubbles, etc., angle of contact, and capillary rise. So my name is Shreyas and welcome aboard. Hi Sushila, Saja, Aisha, Chandan, welcome aboard. I'm very good, Saja. I hope you two are doing good, and please stay safe because it's not safe to go outside. And those of you who do not know me, I'm Shreyas. I'm your captain. You can call me Capto. And Vanakam Sundar. And well, Abhishek, definitely I will definitely reply to your comment from the previous video. Don't worry. Hi Anjali, nice to see you back. Let's get started for today's session. And before we get started, you know what to do. You need to do me a small favor by smashing that subscribe button and smashing the like button down there. So go ahead, do that right now. And yes, Omicron is spreading like crazy, but don't worry, I am there. You know what to do. You can sit at home, relax, just turn on your mobile, your laptop, whatever, and just watch my lectures. You don't know what to do after that. Just practice problems from the books I have recommended, practice the homework questions, practice through Tattva. Make sure you watch all the classes. That's it. All right, let's get going. And so Dharmarajan, this is the last theory lecture of this fluid mechanics chapter. Hello Sarvanti, hello, welcome aboard Nauri, welcome. Hello Gokulnath, nice to see you. Now, there are some students who are still lagging behind in your syllabus. There are some students who have not got the right institute which teaches in English. There are some students who have probably done, but they need that extra jump and want to, practice more problems. And if you have any kind of problems, issues, be it syllabus completion, be it syllabus is completed, be it practice, be it leveling up to top the JEE Mains and Advanced examination, there is one simple solution for all these problems. What is it? It's simple and very easy, and that is at your fingertips. You get all the best teachers without having to travel anywhere. That's the best part about Vedantu Pro, and the reason why I always talk about it is because I believe in it. Because I feel that if this was there in my hand when I wrote my JEE, I would have definitely done better. Because being on the other side, I know what it takes and what you need to do from the student's perspective as well as the institute or the teacher's perspective. And that is one thing I can assure you, that all the Vedantu master teachers, the entire ecosystem is just built with one motive, and that is to make sure that every student improves in his journey. And that's what it's all about. So go ahead, check out the description box. There is a link for the pro subscription. Join it because the pro courses have just started. You can also join my pro courses, and that's absolutely free of cost once you are a pro member, just like Amazon Prime or Netflix, where you can watch anything once you are a pro member. All right, so right now, Saja, there is no lockdown, thankfully, in Bangalore, and I'm guessing for quite some time there will be no lockdown. Let's hope for the best. Thank you, Ashu, for all the love from Kashmir Bacha, and welcome aboard all my warriors. Let's start with the lecture and let's talk about excess pressure. So, here is what happened. There is a beautiful love story out here. There is this Champa. This is Champa, and yeah, she has beautiful hair, you can see, and that is her dupatta. Okay, that is her dupatta. Okay, what is this? This is Champa's dupatta. Perfect. Now, Champa is acting like a romantic heroine in movies. Her dupatta is flying in air. And I have a simple question for you. Let's say her dupatta becomes like this. Her dupatta becomes like this. Okay, just visualize this a little bit. Okay, dupatta, I hope you know, it's like a scarf. Okay, perfect. Now, if I ask you, if it turns like that, and if there are two regions, this is the region 1 where the pressure is P1, this is region 2 where pressure is P2. This pressure is P1, that's where it exerts on all the sides. Pressure is P2 on this region and it is exerting on all the sides over here. Now the question is, if I ask you, out of these two regions, pressure, which one is more? What is your answer? What is your answer? Thank you, Varun. Yes, Saja. So which pressure do you think is more? Is P1 more or P2 more? Come on, my warriors, it's very easy. Is P1 more or P2 more? The dupatta has bent like this. I hope you can see that bending over here like that. It has been bent like this. So wherever, oh Abri Rami B, this is for 11th standard students, even for CBSE, yes, why not? But it will be slightly higher level if you're okay with that. Yes, Ashu, P1 will be more. Perfect. Now, if I ask you, what surface is P1? This side is obviously concave side. And the other side is nothing but convex side. Now, this is not just true for a dupatta, but this is true for everything. So, if you have a curved surface, let's say a film, a soap film, okay, you have a soap film like this, and let's say it bends, and you see that from the side it bends like this, then the pressure on this side, which is basically the concave side, will be always more as compared to the one on the convex side. So this is called as that excess pressure across the curved surface. Excess pressure across the curved surface. So if you have a flat surface, the pressures are equal. The pressures are equal. The moment it is curved, then the concave side pressure is obviously going to be more than the pressure on the convex side. And that difference is called as excess pressure. Excess pressure. Now there is a simple formula to calculate this excess pressure, and we need this formula for solving many questions, because at the end of the day, what is a bubble? What is a drop? What is a bubble in water or any liquid? It's nothing but a curved surface which is separating two different medium. I'll give an example. Just imagine if I take a drop of water. If I take a drop of water, what do you think it is at the end of the day? What do you think it is? It is nothing but a curved surface. This is made of liquid. The air is surrounding it. Obviously, this inner part is on the concave side of it. It's on the concave side of it. So if it is on the concave side, obviously the pressure should be more. And if you notice, the outer part, which is air, that is on the convex side of it. The convex side, the pressure should be less. So the pressure inside a drop, is more than the pressure outside. And surface tension is responsible for that, because the surface tension is going to contract the surface. It's trying its best to squeeze that surface, but it's not able to do much because water is not going to give up. It's not so easily compressible. So at the most, it ends up is just increasing the pressure little bit beyond the outside atmospheric pressure. I hope that makes sense. So what we have discussed till now, that the pressure which is excess on the concave side as compared to the convex side is called as excess pressure, and this is always true for any curved surface, be it of water, be it of air, doesn't matter. Some two different medium being separated by a surface. You can see that. Now the formula for that, let's have a look at it. Number 1, water drop. Number 2, bubble in liquid. Number 3, bubble in air. Students get confused between this and this. How many of you know the difference between these two? What's the difference between this and this exactly? Try to understand that when I talk about a bubble over here, okay, when I talk about a bubble over here in a liquid, there is one concave side and a convex side. The convex is on the liquid, concave is on the air. There is only one surface. Notice there is only one surface separating two different medium. But if you look at this particular diagram, you will realize actually that soap bubble is filled, it's hollow, it's filled with air. So actually there is a layer of liquid in between. There is a layer of liquid in between. Do you see that, my warriors? And you will notice that this part, by the way, this part is air. This thickness will be liquid, and again you have air over here, and that's the formula. I'm just going to put it up over here. So for drop 2s by r, for air bubble also 2s by r, and this is 4s by r. Okay, this should have been, okay, this is actually the total pressure, but I'll get it corrected later on. So delta P will be equal to 2s by r. Fair enough. Can we go ahead, my warriors? Let's get moving. Here's the first question coming up on your screen. Let's do this. The pressure in air bubble just below the water surface is how much? Given surface tension is 72 dynes per centimeter, atmospheric pressure is 10 to the power 5 SI units, and radius of the bubble is 0.2 millimeter. Let's do this math. Now, before we do anything, I feel let's convert all these variables, because without conversion, probably we'll get a wrong answer. So the radius of the bubble is given 0.2 millimeter. So it will be 0.2 into 10 to the power minus 3 meter, correct? Meter, which is 2 into 10 to the power minus 4 meters. Then 72 dynes per centimeter. So this will be 72. 1 dyne is 10 to the power minus 5 Newton. That is per centimeter. So that is per centimeter. So for a meter, it will be 100 times more, because 100 centimeters becomes a meter. So it is these many newtons per centimeter. So when you convert it into meters, so it will be 10 to the power 2 meter inverse. Okay, so this is going to become 72 into 10 to the power minus 3 Newton per meter. Now let's solve this. What do you think is the pressure in the air bubble just below the water surface? So visualize this diagram. This is the bubble. This is just below the water surface. There is liquid everywhere. There is liquid everywhere. How many surfaces are there? How many surfaces are there? Obviously, there is only one surface. Do you see that, my warriors? There is only one surface. And if there is only one surface, what formula will you use? Excess pressure is 2s by r. So pressure inside is more than the pressure outside. That means inside pressure minus the outside pressure will be 2s by r. So the inside pressure will be P naught. What is P naught? It is given. It is 1 into 10 to the power 5 Newton per meter square plus, because this goes over here as plus. So 2s by r. What is s? S is 72 into 10 to the power minus 3 divided by r. What is r? R is 2 into 10 to the power minus 4. 2 cancels, so 10 to the power 5 is 1, 2, 3, 4, 5 plus, like this, 1 lakh. 2 cancels, this goes on the top, it will become 10 to the power 1, so it will become 720. So this will become 1 lakh and 720. So is that there somewhere? Yes. This is all in SI units, so Newton per meter square. Now my point over here is that if you notice, this excess pressure is just 720 Pascal, which is approximately 0.072. Okay, is that right? 1, 2, 3, 4, one more 0. Yes, 0.72 atm. This is very small. This is very, very small. Do you see that? Do you see that? This is very small as compared to atmospheric pressure. That means don't expect a large pressure inside an air bubble. It is more, but it is very slightly more. So that's something which it should remain in your mind. There is excess, but it is not so much. It's in very small quantities, like you can see right over here. Perfecto. Vanakkam everyone. Hello Arun. Good evening. This is one of the best questions. If there are two soap bubbles of different radius and they are connected by a tube, what do you think will happen? Will the air flow from smaller to big? Will it flow from big to small? Will the air flow till the bubbles become of the same size, or there is no airflow? Very interesting question. Let's see how many of you can get this. Figure this out, my warriors. Come on, come on, come on. Think about it. What do you think will be the outcome of this? Okay, I'll give you a hint. The pressure inside is always more than the pressure outside. The pressure in is outside pressure plus, and this is a bubble, so 4S by R. What this means is, if by chance the radius of the bubble is less, like for that one, this number will become big, so the inside pressure will be more. So here the pressure is high because the radius is small. So the formula tells me if radius is small, it's in the denominator, pressure should be high. And when the radius is large, this number is small and the pressure is low. So here we have the low pressure. So what does this mean? That is high pressure, that is low pressure. Where does air flow from? Obviously, it will flow from high pressure to the low pressure. That's how the flow is going to be. So the smaller bubble is going to become much smaller and the bigger bubble is going to become bigger. It's like the rich grows and the poor becomes poorer. So that's the outcome of this, and that's what is going to happen. So I hope that made sense to all of you what has happened. So the pressure here is more, pressure here is less, air will flow from high to low, and that's why this becomes small, that becomes big. That's what is the answer. Option A. It's not C. A lot of people thought C is the option, that the air will flow and they will equalize. That's what should happen in the society. The rich should not become so rich, the poor should not become so poor, everybody should be at the same level. That's what our brain thinks. But that's not how it works. It's the quite opposite of what you thought. Moving on. There are two soap bubbles of different radius, A and B. B is more than A. They coalesce. Coalesce means they meet, they merge. Okay. The radius of the curvature of the common surface is how much? What does this mean? See, this bubble was there, this bubble was there. They meet. When they meet, they will form, a new surface, common surface over here. They will form a new common surface over here. But that common surface won't be flat, it will be curved. And why will it be curved? Because these bubbles are of different size. Different size means different pressure. Different pressure means one will be concave, one will be convex. I hope that makes sense. So that's why the common surface is different. Let's find this out. Which side is more, which side is less? First, let's assume that the outside pressure is P0. Fair enough. Now, the pressure in this bubble, okay, in this region. Which region am I talking about? I'm talking about this region. In this region, what will be that pressure? We all know which formula to use. It's a bubble, it's a film. A film has two surfaces. Two surfaces means 4S by R. So the pressure over here will be P0 plus 4S by radius. Radius is B. That's the pressure here. Cool. Next, what about the pressure in this region? in this region. Obviously that will be also more than the outside pressure over here, and that will be P naught, but it will not be 4S by B, it will be A. So 4S by A. Now if I ask you, who is big? This is big or this is big? Not size wise, pressure wise. Well, size wise B is bigger, so this term will be smaller, so this pressure will be less. So clearly this pressure is less than that pressure, and that's why if this side pressure is more, you can see the common surface has bent. Did you see that? Thank you Shreyas so much. Thank you Sarayu Deshpande. I'm so glad, and you got noticed because of your hearts. Keep watching, stay tuned, and we'll excel together. So the common surface will bend, and how much is that radius of curvature can be found by, remember, if there is a new radius of curvature here, that can be found by finding the pressure difference across two surfaces. This is a film, don't forget that. That's a common film. That's a common film. So this pressure minus this pressure will be, I'll repeat. So this pressure P naught plus 4S by A minus P naught plus 4S by B. Why is this? This is because this one is on the convex side and this one is on the concave side. This will be equal to 4S by small r. 4S by small r. Why 4? Because it's a film. Film means it will have two surfaces. Two surfaces, one on that side and one on this side. That's why 4S by r. And now it's just a matter of solving this. P naught goes. So you will have 4S by A minus 4S by B is equal to 4S by R. 4S goes. So B minus A by AB is 1 by R. So R will be AB divided by B minus A, which is option A. Did you guys get it? So what are the concepts involved? Two bubbles, they will have more pressure inside. They'll have more pressure inside. How much? By amount of 4S by the respective radius. The one which has small radius has more pressure. So that will push the common surface like that. And then the difference between their pressure will be given by 4S by R because there are two surfaces. As simple as that. That's it. Perfecto. That's option A. Moving on to the next one. Now that we have spoken about bubbles, we should also talk about how, this can probably create some really interesting things. That is more specifically, capillary effect. And you will see how capillary effect is related to pressure difference across curved surfaces. By the way, you would also remember from my previous class, I have already done problems involving energy and bubbles in my last class. Although I had not taught you bubbles and drops exclusively, but that topic was independent. So if you want more problems on bubbles and drops, where bubbles meet, how much energy is lost, etc., please watch the last class. Okay? Great. Now, here is the thing. Angle of contact. You would have seen that when water falls on a frying pan, it behaves differently than the way when water falls on the floor, and it behaves differently when water falls on your hand. For a non-stick kind of a vessel, the water forms like a drop, like the one it forms on a lotus leaf. Something like this. Probably when it falls on a sticky surface, maybe your hand or I don't know, maybe something else, you will see the water drop shows this kind of behavior. So, do you see the nature of the drop changes just on what kind of surface it falls on? So the liquid makes different angles with the solid surface every time. Have you also noticed whenever you fill water in a small test tube, have you seen that there is a kind of a meniscus, there is a curvature over here, there is again some angle made over here. So why is that angle there? Why is it that you have different angles made with different liquids and different solids? We are going to explain that. and that angle is called as angle of contact. So simply put, wherever the liquid meets the solid, look at this, the liquid meets the solid, at that point you draw two tangents. You draw tangents, one to the liquid surface, one to the solid surface. Now you have two ways of measuring the angle. One, you can measure this angle, one you can measure this angle. Don't measure this angle. Like, sir, why? So by definition. So what's the definition? Always measure it inside the liquid. Where will you measure it? Always measure it inside the liquid. Keep this in mind. So this is the point where liquid meets the solid. Draw tangent, measure it inside the liquid. Draw tangent where it meets. Measure it inside the liquid. So here it is obtuse. Here it is perpendicular, and here it is acute. So it depends. This angle of contact depends on liquid. It also depends on the solid. It depends on both these things. Okay, it depends on both these things. Perfecto. Now, why does this come? This comes because of exactly this diagram, and this diagram explains the two important forces in liquids and solids: cohesion and adhesion. What is the meaning of cohesion? This diagram explains it. Look at this. This is a water molecule. This is another water molecule. Do you see they are holding each other's hands? So a water molecule will form bond with other water molecule. When they form bond, there are forces. The force between similar molecules is called as cohesion, but this is some other material, maybe glass, maybe silver, maybe gold, maybe cement. Water might be in some container, maybe it's made of plastic. So it might form bonds with that. Yes, Arun, it will also depend on temperature eventually, because the nature of the liquid will change based on the temperature. So indirectly temperature will affect the liquid or the solid, one of them or both of them. Yes. So what I am trying to say over here is the bond formed between a liquid or materials of two different kinds, that is called as adhesion. So now why are we talking about adhesion and cohesion out here? You might be wondering. I'll give a simple reason for that. Okay, let me just get rid of this diagram and just imagine this. Just imagine this. These are your container molecules. What are these black molecules? These are your container molecules, okay? And these are your water molecules or liquid molecules. Ideally, the liquid should remain flat when placed in a container. That's what one would expect, right? But let's just say that the bonds which are formed between the liquids themselves, the bonds which are formed between liquids, so basically that cohesion is, let's say, weaker than the adhesion. Adhesion means the bonds which are formed between the solid and the liquid. These bonds are stronger. If these bonds are stronger, then this molecule or this molecule will be like, wait a minute, I am helping this guy and I am also helping this guy, but they are giving me weak bond. Instead, I might just jump over here. I can just jump over here, and you know, if I jump over here somewhere like this, if I go like this, and this guy will also think if I jump over here, and these people will think if I jump over here. So if these people jump over here, then you will have a stronger bond being formed. Sorry, not this one, but yeah, this one. All these stronger bonds will be formed. So the adhesion is strong. Their attractiveness towards those container molecules will be more, so they will immediately jump up. And that's why you will get a curved surface like this. You will get a curved surface like this. Is that understood, my warriors? You're going to get a curved surface because these molecules are immediately going to jump up. Now the moment these molecules jump up and start forming adhesive bonds, what you're going to see? You are going to see that the solid is here, the liquid is like this, and this, if you draw tangents, look at this. If you draw tangent to the liquid and if you draw a tangent to the solid, you will see this is the angle which is there inside the liquid. So this is basically your angle of contact, and this angle of contact is acute. So this is this scenario, the angle of contact is acute. So in this situation, you will see the cohesion is weak, adhesion is strong, it sticks. So that's why the liquid surface gets pulled. It prefers sticking to the surface than sticking with each other. That's what happens. I hope this is clear. So the point over here is that when adhesion is more, the liquid ends up sticking. Wherever the solid is, it will spread on that solid surface. But when adhesion is weak, like in this case, adhesion is weaker than cohesion, you will see it will make an obtuse angle, because if you look at the molecules of that container, which are the ones in the black, they will not be of any use for these liquid molecules right over here. These liquid molecules will not like these bonds made with this black color molecules. So these liquid molecules will be like, okay, let me just go and make a bond over here. So these molecules are basically going to mingle among themselves. They are going to repel, or they will not prefer to stay there. So that's when adhesion is weak, cohesion is strong. And basically when adhesion and cohesion both are roughly similar, you will see that the angle of contact is 90 degrees. So those are the three different scenarios. Is that understood, my warriors? Is that understood, my warriors? So when adhesion roughly equals cohesion, you will see the angle of contact is 90. When adhesion is very strong, it is acute, and adhesion is weak, molecules prefer to stay together, they will round up, and the angle of contact will be obtuse. Okay, perfecto. So very good, Chandan. Hello Vijayvardhan, hello Nikhil, hello, welcome, long time Nikhil, I hope everything is fine. Okay, so the different examples of acute and obtuse angle, I want to give it to you. So water in glass makes an acute angle, but if you have ever seen a mercury thermometer, observe it closely. Have you seen? How many of you seen? Raise your hand. If you've seen a mercury thermometer, it makes an obtuse angle right over there, and it looks something like this. This is the obtuse angle made in the mercury thermometer, because mercury molecules prefer to be with each other as compared to the glass, and these water molecules tend to attract the glass molecules as compared to themselves. That's why you get a concave meniscus upward. This is concave up meniscus for water in glass. This is convex up, convex is up for mercury in glass. Very good, many of you have raised your hands. And this exactly causes the rise or fall of liquids. This is exactly the reason. The moment the liquid loves the solid, it's going to climb over it. Look at this. Don't you see their love story? Are you seeing that chemistry right over here? The liquid molecules love the glass molecules. They start climbing up. They love them. But here, these liquid molecules are like, I don't like you. I don't like you. This glass molecules, I want to stay away from you. Stay away from me. So it's as if they want to stay away. It's like, oh, it's making a sad face and going down. Do you see that? Okay. Yes, so that's what it is. So here, think of a very sad face. It doesn't like this. Here, it's very happy, climbing up. Now you'll be like, sir, why doesn't it keep on climbing like this? Why won't it climb? Obvious. If it keeps on climbing like that, who is going to increase? Who is going to pay for the increase of potential energy? Somebody has to pay, right? So these molecules saw happiness in making bonds with the solid molecules. So they immediately start climbing up. But then they later on realize, if I have to climb up, I have to lift all these kids down there with me. Till some time, they are going to see that benefit. They will make the bonds till some time. They will like making those bonds between the solids till some time. But then, beyond a point, how many kids, how many molecules, these blue water molecules are you going to lift? They will give up, and that's when it stops. I hope this is clear. So in the other case, it won't keep on repelling down, because if you keep on pushing it down, these molecules have to come up. That is also not good, because if you push this down, this has to come up. So who is going to pay for their increase? So that's another story. I hope that makes sense. So by the way, also remember, whenever the angle is acute, it's also said that the liquid wets the solid. That's how you write it. And when it is obtuse, then you say the liquid doesn't wet. Okay, it doesn't wet the solid. So it doesn't wet the particular solid. It repels from it. It is phobic. Okay, and these are the scenarios. Now we want to calculate how much is this capillary. This is a capillary, by the way. If you are wondering what's a capillary, capillary is a thin tube. So this thin tube over here, this tube is called as a capillary. Okay, and we are going to study the rise and fall of liquids in a capillary. Just to give you some data, for water, okay, and glass, the angle of contact is 8 degrees, 10 degrees, like that. That means it's very small. And if it is very pure water, pure glass, it's very close to 0 degrees. Okay, so 0 to 10 degrees, 18 degrees for water with glass. But water with silver gives you 90 degrees. Water and silver, oh my god, silver container. Okay, it's difficult to get, but yes, if you have one, you can try it out. The angle of contact is 90 degrees. And when water is put, this is glass and mercury, it is 135 degrees. So obtuse, like we all know, for mercury and glass, it should be obtuse angle. Okay, great. So keep this in mind. If this is clear, give me a thumbs up. Like the capillary in human body, yes. So capillary is thin vessels, blood vessels, thin tubes. Oh, by the way, do you know, in humans, the blood can reach the top, or even in any other animal, the blood or the liquids, fluids can reach the top because there is a heart, because there is a pump. The water in your house reaches the top floor because there is a mechanical pump, electrical pump. But in plants, is there a mechanical pump? Is there some motor? Or do the plants have heart? Now don't take it literally. I mean, like, I'm not talking about like, do plants have feelings? I'm talking about, does the plant have a heart to actually pump that water? What do you guys say? Yes or no? What do you guys think? Actually no, but still the water reaches the top. How is it that the water reaches the top? And the answer for that is exactly this. Look at this. If there is a capillary kind of action in plants, the water can be pumped up through that capillary. No, not exactly. Yeah, there are two different processes. One is osmosis and all of that. But yes, there is one more effect, and that is called as capillary effect. So if there are fine tubes, they are called as xylems in plants. And in these fine tubes, if the water can enter and it sticks to it properly, then it will rise up by a good amount. And that's how the plants are able to ensure that the water reaches sufficient heights. That's what happens, not root pressure. No, there is nothing called as root pressure. Okay, great. Yes. Yeah, beautiful. And this is exactly demonstrating your capillary effect. Take a cloth, take 2 buckets, 2 glasses, and a cloth which can be easily wet, very fine pores. You will see the glass which has less water, you will see the water starts filling up, and the reason for that is tubes inside these pores. This cloth is made of pores, tiny tubes. They love water. So the moment they see water, they will drink it. It's like it's sipping on it. It loves it, just like how you love juices. So it loves those water molecules. It sips it, and they start attracting the water molecules. And once the concentration of water increases, you see they will have to drain it out. So they will drain it out over here. That's what happens. And yes, the water, once it gets accumulated here, the potential energy increases. So the water will have to eventually flow down. Yep, that's how it is. Perfect. Oh, Chandan, you have already tried it with juice. That's good. Hello Sundara Murthy. And those of you who are joining in late, I hope you have already hit the subscribe button, because then you will not miss the next class. And yes, number 2, I hope you have already smashed the like button. In case you haven't, do that. Okay, let's talk about it. Capillary rise. Okay, let's do this, my warriors. Why does liquid rise in a capillary tube? Beautiful, beautiful scenario. Let's look at all these points out here. This is a capillary. You insert it in a liquid. You see suddenly the liquid jumps up till a certain height h. A is a point on the concave side of the surface. B is a point on the convex side just below the surface. E, D and A are the points just below the water surface. C is a point just above the water surface. Everything is like very obvious. If you zoom onto this diagram, if you zoom onto it, then it looks something like this. This is the curved area. This is the curved area. That point B is below. That point A is on the top. That curved area will be a part of a big sphere. Correct? That curved area will be a part of the big sphere. The center of the sphere is O. What is the center of this hypothetical sphere? O. It's like the center of curvature in optics. The radius of that imaginary sphere is R, capital R. And that is quite different from the radius of the capillary. I want you to get this very clearly. Understand, if this is my tube, okay, then this is R, that is the radius of the tube. This is the radius of the capillary, the cylinder. But my surface of liquid itself might be curved, and that if you extend it, that radius is the radius of curvature. So there are two different radiuses. Got it? Now, once you have understood this, I hope you all agree to this point that the pressure on the concave is always more than the pressure on the convex. So pressure on concave is more than convex. Now if you notice, there is a concave convex surface which is created. In fact, there will be a surface here as well. Okay, and let's say A, B, C, D, E. Okay, I don't know why we have two A's over here. Okay, anyways, now think over here, the pressure is actually atmospheric pressure. The pressure at this point is actually atmospheric pressure, correct? Now, at this point below, because it is on the convex side, shouldn't the pressure be less than the atmospheric pressure P? The pressure inside should be less. But think again, here, which is C and D, that's a flat surface. At these points, the pressure is just P. At these points, the pressure is just P. And at the same height, here the pressure is low. What does it mean? At this point, the pressure is P. At this point, the pressure is less than P. So the liquid will immediately flow over here. High to low. It will flow and it will push it up. It will flow and it will push it up. I will repeat over here again. Observe this carefully. At these 2 points, the pressure, it's just below and just above the water surface. It's a flat surface, so it's same. This is all P. At this point, it's P, but when you have a curved surface, just below it, the pressure is less. So the liquid will immediately flow from high to low, and once it flows, it is going to push up this surface. And that's why the water rises. So what happens eventually? What happens eventually is that the water will keep flowing. This is the diagram before, this is the diagram afterwards. Think of it like that. So what will happen eventually is that the water will go up till such a height where here at point A, okay, I'll just write it down over here. At point A, the pressure is atmospheric pressure. Okay, this is the atmospheric pressure. At point B, the pressure is less. So it's less by the pressure at point A by a factor of 2s by radius of curvature. Now when you go from B to E, When you go from B to E, the pressure will increase because of rho g h effect, hydrostatic pressure. So the pressure at point E will be pressure at point B plus rho g h, which is nothing but P minus 2S by R plus rho g h. Now comes the last part. At point E, which is at the same level as that of D, at point E, which is at the same level at D, the pressure should be same as that at C, which is also P. C, D, P, all these are same things, same height, same pressure. What does it mean? Just look at this math. This is P, this is also P. Cancel this out. Cancel this out. Just take 2S by R on the other side. Just take this 2S by R on the other side. So 2S by R will be rho g h. Correct? Rearrange, you will get H is equal to rho g R by, oh sorry, my bad. H is equal to 2S divided by rho g R. That's what you're going to get. So you can see surface tension, density, gravity and the radius of curvature all play a big role in determining how high the water will go. So the water goes up till such a height where the pressure at these 2 points equalizes. Think of it this way, due to the curvature the pressure drops, but it again increases because of the rho g h effect. So if the drop is same as the increase, then the pressure is nullified. So that's the height till which it moves up. Got it? Got it, my warriors? Okay, the last thing over here. Draw tangents. We have just defined angle of contact. Draw tangent to the water, draw tangent to the solid. This is angle of contact, theta. If this is theta, this is 90 minus theta. This is again theta over here. If this is angle of contact, this is 90 degrees. So this is 90 minus theta. Again that is 90 degrees. This is theta. So do you see a right angle triangle? Remember that O was the center of that big circle, R was the radius of the circle, small r was the radius of the capillary tube. So from this, can you see R is the hypotenuse, cos theta is equal to the small r? That's it. So just substitute the value of capital R over here. So what will you get? 2S by rho g. Instead of capital R, put it as R by cos theta. So it's going to become 2S cos theta divided by rho g r. So this is the more frequent formula, because generally you won't know the radius of curvature, but you will know the radius of the tube. You will know this radius. That radius will be known, that small r. Is that okay? Now I have a simple question for all of you. Simple question for all of you. If theta is acute, like water in glass, is the value of H going to be positive or negative? Think about it. Cos theta, cos 0, cos 10, cos 20, cos 50, cos 70, they are all positive. So obviously H will be positive. If theta is 90 degrees, cos 90 is 0. So H will be 0. So that means water in a silver container which has an angle of contact of 90 will neither rise nor fall. So H is 0. And if theta is obtuse, then the value of H will be negative. As simple as that. So when theta is obtuse, the value of H will fall and it will go down. That's it. So this formula can be used for both rise as well as fall. Negative just signifies it's not going to rise up, it's going to fall, just like mercury in glass. As simple as that. Keep all of these things in mind. So I have put up all the derivations just for you, just in case you need it. So it's all there right over here. I have put it up in a beautiful way. So H is 2S cos theta by rho g r. Let's start solving some questions. If you guys are ready with it, ready for some questions, that's the end of the chapter then. But before that, look at this beautiful graph, or rather I would say picture. In fact, this is also a capillary, this is also a capillary, but as you go here, the radius decreases. And do you see this over here? R is below, H is on the top. If R decreases, H increases. So if the capillary is tiny, the height increases. So this is exactly what it shows. The height is inversely proportional to r. Height is inversely proportional to r. You can see that right over here. Perfect graph. Yep, very good. Let's move on to the question. Yes, Nikhil, I have done it. Flash series last year, 0 to hero, so many things. Okay, when a long glass capillary tube of radius this much centimeter is dipped in a liquid, the liquid rises to a height of 15 centimeters within it. If the contact angle between the liquid and the glass is almost zero, surface tension in millinewton is how much? Given the density, given G, give the answer to the closest integer. Let's have a look at this. So what do we need to do? We need to find out the surface tension, right? And what else do we need? I guess the radius is given. The height is also given. Perfect. So let me start with h is equal to 2s cos theta by rho g small r. But I need to find out s. So s will be h rho g r by 2s cos theta. Let's start substituting all the values. So h, what is h? Height is 15 centimeters. So 15 into 10 to the power minus 2 into rho is 900. So 900 over here into g, which is nothing but just 10, into radius. The radius is 15, that's centimeters. So 3 and then 10 to the power minus 5 meters. I hope you guys got that. There are 3 decimals here. So 10 to the power minus 3 and converted into meters, 2 more decimals, so 5. So 10 to the power minus 5. That takes care of the numerator. Denominator, you have 2 into s. Oops, I did make a mistake. Oh yes, I shouldn't have put 2s cos theta. I just had to put 2 cos theta, my bad. I had to find s, my bad. So 2 into cos theta. What is cos theta? Cos of 0. So cos of 0, which is nothing but 1. Yep, there you go. Just solve this, you'll get the answer. Yep. Hello Ananya, welcome aboard. So 15 into 15, that's 225, and then 225 into 9, you can do it. Okay, so all you will get over here is 225 into 9 divided by 2, and count these zeros over here. These 2 will get cancelled. You will have 10 to the power minus 4. Just do the math and see how much is it coming out to be. Yes, Arun, I just took care of it. Don't worry, yep, just I took care of it. So 225 into 9, just do the math. 45, come on. 18 plus 4, come on, do the math. Come on guys, my warriors, figure this out. 22. Okay, just check this out. If you are getting very close to this number, yep, just check this out. If you are getting this, 2025 divided by 2, I believe, into 10 to the power minus 4. So this will become 1012.5 into 10 to the power minus 4. Just check this out. If this is what you're getting, okay, just check this out. Yep, everyone. Arun, is it 0.11? I doubt it. Just check this out. Is it 0.11 or 0.101? I think it is 101. I think you missed 10 somewhere. Just check that out. Okay. So it should be 101, I believe. Yep. Yeah, 0.101 millinewton per meter. Okay. Perfect. All right. Let's move ahead to the next question. Moving on. A capillary tube of this much radius is submerged vertically in water and 40 millimeters of its length is outside water. Very good. Then the radius of curvature of the meniscus will be. This is not an easy problem. Okay, no problem. Happens, Arun. This is a very interesting question. Many students do not understand the criticality of this question. See, usually when you have a capillary, the liquid will rise till certain height. Let's say till this much height. Okay, but what if the tube is itself insufficient to make the water rise till that height? Are you able to understand? Usually the water might, or any liquid may rise till certain height, but what if the tube itself is incapable? It's of limited height. So then once the liquid reaches here, the curvature won't be same, the curvature itself will be different. That's what will happen. So the point here is, if the radius of curvature here was R1, you will see it will have a different radius of curvature in order to maintain that pressure difference. You can think of it this way. Our height rise formula was 2s cos theta by rho g small r, which you can also write it as 2s by rho g capital R. Now think about it. If S, which is the liquid, is the same, density is the same, G is the same, if you have different heights, here you have H1, here you have H1, here you have H2. If heights are different, the only thing which can be different is the R, which is the radius of curvature. Is that making sense? So the radius of curvature will adjust itself to make sure that their other things are constant. So can I say from here, H into R, which is 2s by rho g is nothing but a constant. H into R, which is nothing but 2s by rho g, is a constant. Everybody agrees with this statement? Perfect. Okay, now let's solve the question. Here, understand, the tube above water is 40 millimeters, and the reason why they have given it is because many students fail to understand, because the tube is actually insufficient. It's not sufficient for the liquid to rise up. Okay, so once it reaches till 40 millimeters, it's going to just change the curvature. So what you should understand is that H1 R1 will be H2 R2. This is the second case. This is when it is sufficient. This is the sufficient condition. This is the insufficient case, when the height is basically how much? 40 millimeters. Now when it is sufficient, what can I say? H1 R1, I know it is 2s by rho g. H1 R1 is basically 2s by rho g. This is equal to H2 R2. Now just start substituting the values. What's the value of S? The value of S is 75 into 10 to the power minus 3 divided by rho. What is rho, guys? It's water, right? So it is just 1000, and G is nothing but 10, is H2 R2. Height is 40, so 40 into 10 to the power minus 3 millimeters, it is converted into meters, into radius, which is R2. Okay, let's do the math. So what do we have over here? Just this 2 goes with this 42 over here. So bring that 2 down. So 75 by 2 into 10 to the power minus 3 on the top. Here you have 10 to the power 4, and this 0 and this 10 to the power minus 3 will make it 10 to the power minus 2. Bring it down. So 10 to the power minus 2 over here. This is equal to R2. So solving further, let's see what do we get. R2 will be 75 by 2, which is 37.5 into 10 to the power minus 1. This will become 10 to the power minus 5 meters. Yes, 10 to the power minus 5 meters. You can also, just check this out. Is this coming out to be 10 to the power minus 5 meters? Sushila is saying option C. Is it, just check out all these calculations, my warriors. 37.5 into 10 to the power minus 3. So let's just take 2 decimals inside, because everywhere I'm seeing 0.37. So it is 0.375 into 10 to the power minus 3 meters, which is 0.375 millimeters. So if you round it off to 2 decimals, I think this should be the answer. Yes, Sushila, you are right. Perfecto. Very good, bacha. Everything is fine. Okay? Is that okay, my warriors? That's the answer. Yep, it is. Here is the next question coming up on your screen. A capillary tube, when immersed vertically in a liquid, it records a rise of 3 centimeter. But if the tube is in the liquid at an angle of 60 degrees with the vertical, then what do you think is the length of the liquid in the column? Let's have a look. Okay. First of all, if you immerse the tube vertically like this, the liquid goes up till this height. But if you immerse the tube this way, then should it be that I should just take the same height and then mark it here, or the liquid will still rise till the same height? Now the answer for that is, doesn't matter how the tube is, the liquid will always fill till the same height, because pressure depends only on the height, not on the horizontal distance. Pressure depends only on the height. So basically whatever is the horizontal displacement does not matter. So the point over here is that no matter how much bent the tube is, you will see the liquid will always rise till the same height. Okay, same height from the base, because that much pressure difference has to be created because of the curved surface. If the curved surface is creating some pressure difference, that needs to be compensated by the height rise of the capillary. So what is given in the question? In a normal situation, this is 3 centimeters. The question is, how much is this? How much is this? Let's say this length L. So it's also mentioned this angle is 60 degrees with the vertical. So L cos 60 degrees is 3. So L by half is equal to 3. So L is basically 6 centimeters. So that option is there. These kind of questions do come in JEE. I hope this is clear. Yep, understood, my warriors. Very good, very good. Now that's the end of fluid mechanics. We have to start waves in the month of January. Before we start waves, we are going to do a lot of sessions for KVPY, and also you are free to attend the sprint sessions. Now please do join the Telegram channel and you will get the solutions of these homework questions. This is the first homework question for you on today's lecture. This is your second homework question. You can take screenshots, solve it later on. You'll also get it in a PDF. This is your third homework question. And remember, this is where you post the answers, and let's have a look at the students who have posted the answers last lecture. There we go. Where are we? So videos, you go here. Do you see lecture number 5? Yes, surface tension. Just go over here and you can go down. These are our amazing students, Ishpreet, Chandan, and yes, Anjali, Sushila. Yes, my God, thank you so much for all the hearts. You deserve a heart, bacha. Very good, Siva. Very good, Sushila. Very good. Nurture and Pathfinder, is it discontinued? No, it's not discontinued. Okay. Thank you, Ramya. I read this comment. It really made my day. I'm so glad you're waiting eagerly for the next class of Modern and Thermo. And very good, Yash. Congratulations. Now, also, when you're watching this video, you will see in the description box when you want lectures from me. So that's where you get it, in the description box. JEE 2 years program. Just click on this, because a lot of students keep asking, sir, which is your batch? Sir, where do you teach? Can I attend more of your classes apart from the ones on YouTube? I really like the way you teach. I want to understand more physics concepts. And not just me, so many amazing master teachers just like me on our platform. Now everybody can't come on YouTube, and not everybody on YouTube can take all the classes everywhere. So you have very good pool of amazing teachers, and you get access to these quality teachers right at your doorstep. I wish all these things were there during my time, but you are very lucky generation. Not only is your 11th standard syllabus going to be completely revised, but also you will have the direct entry into the 12th standard batch, which will start in March end. And most likely I will be there. So I'm pretty sure you guys want to learn under me, and the only way you can do that is by joining the pro subscription right now, because if you join later on, then you might not get entry into my batches as well whenever they start. So apart from that, you get other course benefits like KVPY, Olympiads. All the preparation for any kind of examination is there over here, even boards. So you don't have to subscribe to multiple subscriptions or multiple institutions. So there are 3 versions: Light, Classic, Plus. Everything is same. You get test series, assignments, everything is same except for doubt solving and personal mentorship. So if you want doubt solving, go for the Classic, and if you want personal mentorship, go for the Plus version, where you have a personal guide. The price differences are nominal. Even the highest package price is 97,000 for 2 years, which is less than half the price for any regular coaching institute. Our smallest package is 53,999 for entire 2 years, and you can avail it for 15 days. You get more 15 days free for just 1,350 rupees. Just click on this link and you save a lot of money through this coupon. You save even more when you buy the entire subscription. Obviously, you have multiple options to pay from. So that's how you enter the subscription. And that's why you should join the subscription, because it's very cheap and you get everything under one roof. I can see all the hearts right over here. Thank you, Hariharan. Abhivya, thank you. Thank you, Sushila. Thank you so much, everyone, for joining in for today's class. I'm pretty sure you have learned a lot. Fluids is officially over. We will definitely have more problem solving classes. Please attend the sprint classes. It's exactly for you, apart from your seniors in 12th. Also attend the KVPY classes. We will start with waves in the next year. All right, not now. Good night. Have a great time. Keep attending. See you in the pro subscription. Please keep studying and please take care of yourself, my warriors, and have a great time. See you again in the next class. Bye bye. This was Captain Shreyas and I was going live. Hasta la vista.